Estamos en vivo.
Hello, everyone. We are going to start the fourth session of this meeting. The first speaker of this session is Manuel Gadela from University of Valladolid in Spain, and he's going to talk about rich Hilbert spaces and unstable quantum system. Please, Manuel, when you want, and start.
Thank you, Marcelo. First of all, I want to thank the organizers to have invited me to give a little talk in this meeting, and I'm very happy because the organizers are good friends of mine, and Federico Holic, Olimpo Lombardi, Marcelo, and so on, and Sebi are very good friends of mine, and this for me is a pleasure to participate in this meeting. So I'm going to, in front of my computer, and my talk is, as Marcelo has said, is regular spaces and unstable quantum systems. And let me start with speaking about quantum resonances, which is the main subject of the present talk. Quantum scattering resonances in non-relativistic quantum mechanics are quantum systems which decay, so are unstable quantum systems. They are produced by a potential in which the effect of trapping a quantum particle in a localized region for a time much larger than this particle would stay if that did not exist. If you can see my blackboard, the procedure is something like this. An incoming state comes to interaction region, and then the particle representing this incoming state is trapped in this region for a time much longer than the time it would stay if this potential did not exist. And then after a while, the particle escapes of the interaction region and evolves freely. This is the notion of potential resonance scattering. In fact, the case systems are usually look at the second half of this procedure, ignoring the procedure of constructing avoiding the procedure of trapping the particle, and therefore the procedure of constructing the unstable system. This is the idea. So that in order to have a quantum scattering resonances, we need a Hamiltonian pair, a free Hamiltonian plus a potential. This potential is this potential B. Here I draw it as localized, but it should be, I mean, it's not necessarily being strictly localized, strictly of compact support. V is the potential responsible for the formation of the resonance. In the analysis of quantum scattering resonances, we may consider two different steps. First, the process of creation of the resonance, and then the process of decay. They are substantially asymmetric. Studies in quantum scattering resonances have been usually focused on the decay, ignoring, of course, the process of constructing the resonance. There are two. What is the definition of proper definition of resonance? We have several definitions which are not all equivalent in all cases. They are equivalent in many cases, in many practical cases, but not always equivalent. And the process and the study of the equivalences between all these definitions has still to be done because it's not thoroughly settled. But we can distinguish two possible definitions of resonances. Two types of definition of resonances. The definitions given by physicists and the definitions from a more mathematical point of view. What do physicists say about resonances? How do physicists define resonances? There are several possible definitions. First, resonances are characterized by large time delays. This is the difference of times between the time that an incident particle stays in interaction region with and without interaction. time delays are measurable. And there's a formula to measure them that has been stated for many years ago in the 30s by Wigner. Then another sudden bump in the cross-section around a given energy, ER, and having a width given by gamma. The mean life is stuff equal to 1 divided by gamma. Another definition is a sudden change of the phase shift around the given energy ER. And then the scattering amplitude of the wave function in the representation of the energy has to be a Lorentzian shape, which is precisely this formula number 1. Observe that in general, the Hamiltonian is semi-bounded, so that the possible values of the energy are bigger than a minimal threshold. Usually you can settle this threshold equal to 0. So that this, for some reason, this Lorentzian shape is not a realistic formula. And then, once we have viewed very quickly, because this definition go rather further. The definition given by physicists, let us go to the definition given by mathematicians. And there are essentially two. Definition number 1 has been given in the book of Ritz-Simon, and assume that there is a dense subspace or vector Hilbert space such that for any psi belonging to this dense subspace, we have these two functions, the functions of the complex variable zeta. And assume that these two functions have an analytic continuation through the real axis. Assume that, or simply through the spectrum of both Hamiltonians. The Hamiltonian H0 is a free Hamiltonian. Hamiltonian H is the total Hamiltonian, including the potential. Assuming that these two functions have analytic continuation through the real axis. Assume that the first function involving the free Hamiltonian H0 is analytic at a certain point, sit R equal to ER minus a positive imaginary part. But on the other hand, the other function involving the total Hamiltonian shows a pole at this point. Then we saw that Hamiltonian pair exhibits a resonance at the point zeta R, where ER is the resonance energy and gamma is the inverse of the mean life. Then there is another mathematical definition of resonances, which is more popular to physicists. Let the SK or SE be the S matrix, the S operator, in the momentum and energy representation, respectively. Assume, for instance, the SK in the momentum representation can be analytic continuate to a meromorphic function in the whole complex plane. Then we define a resonance into one of these two equivalent forms. First, pairs of poles of the analytic continuation of the function S of k in the momentum representation located symmetrically with respect to the negative imaginary axis. You can see my blackboard. I have depicted a typical S matrix in the momentum representation, so that the resonances are pairs of poles located in this form. These are Balm states. In some cases, some potentials, they have another features over here in the positive imaginary axis, and this we may have anti-Balm poles in the negative imaginary axis, and this is the most popular. And also, if we work in the energy representation, pairs of complex conjugate poles of the analytic continuation of the S matrix in the energy representation across the positive real axis. In the language of Riemann surfaces, the poles of SE on the second sheet of the Riemann surface correspond to the transformation k equal to square root of 2 mass times the energy. Each of these pairs are localized at two complex conjugate points. Now, this is rather abstract, and let me introduce, well, it's very well known since 53 years ago, but it is the so-called Friedrichs model. And what is the Friedrichs model? The Friedrichs model is an exactly solvable model, and very rather simple, showing resonances. The idea to create a resonance is to produce an interaction between a bound state and an external field in such a way that the bound state becomes unstable. We define the Hamiltonian pair as follows. The free Hamiltonian H0 already contains the bound state and the environment, or the external field, whatever you want to call it. And the total Hamiltonian intertwines bound state and environment, or external field, as you prefer. And then using the definition number one, the definition that is more like that more appreciated by mathematicians, we may find the resonances in this model. The resonances are given by partial complex conjugate of the analytic continuation of the formula given by 5, which is the resolvent of the so-called total Hamiltonian. And then this can be written in terms of a function, and this function has the form given by the formula number 6, second formula in this transparency. This function has the positive part of the real line as a branch cut. Under some properties of the form factor f omega, the function which appears under the integral sign, it admits analytic continuation through this cut and has a pair of complex conjugate poles located on the lower and the upper half plane respectively. Well, this we can construct we can obtain these poles, and these poles has the form given by the upper formula in this transparency. This gives a relation which is analytic in general, at least for small values of lambda. If lambda goes to 0, we obtain the resonance goes to the value of the bound state of the free Hamiltonian. Then, what is the gamma state? The gamma state is the part of the decaying state which decays exponentially. And here is very simple, and it is in general defined as eigenvectors of the total Hamiltonian with complex eigenvalues which coincide with the resonance poles. Be careful what I have said, because complex usually in Hilbert space self-adjoint operators do not have complex eigenvalues. What happens here? Happens here that you see in the formula below, it is a rather strange formula. It is this denominator means it can be it means cosine principal value plus some term, and it is indeed not really a proper function. It is some kind of distribution, but I will explain it later what this distribution is. In fact, there are two possible gamma states. The decaying gamma state, which is the eigenvector of the total Hamiltonian with one of the complex poles that characterize the resonance, and the other one corresponds to the complex conjugate. The decaying is called like that because it decays exponentially to the future, and the growing is called like that because it grows exponentially to the future and decays exponentially to the past. I have said that here there are several possibilities of constructing, let's say, products between the gamma vectors which and some of them may be defined, some of them cannot be defined, but this is not important at the moment. I said that the gamma vectors, or vectors that represent the decaying part of a resonance, is I have to say that the resonance decays in the most period of time approximately of exponential form, so that the gamma states are not a bad approximation for spectral state for resonance. And let us forget about what happens for very short times and very long times, where the deviation of the exponential decay law appear. But let us concentrate ourselves in the point of the meaning of gamma vectors. Gamma vectors cannot belong to the Hilbert space because Hamiltonians are self-adjoint operators. And then how to define this gamma vector? We define this gamma vectors by defining the Gelfand triples. The Gelfand triples are, as a matter of fact, terms of the spaces in which the intermediate spaces Hilbert space, where the Hamiltonians live, and these Hamiltonians can be extended to a bigger space that we represent here. By, it is the space in the left, in the right, which is a space of some kind of distributions, so that we can extend the Hamiltonian to this bigger space, and then these gamma vectors are really eigenvectors of the Hamiltonian in this extension of the Hilbert space. I want to skip the details because otherwise I will not finish my talk. But we can construct. There is a typical way to construct this extension by using a duality formula like which appears here in number 12. It is interesting to insist that there are two gamma states, each one corresponding to one of the elements of the pair of poles given the resonance, and it is also interesting to note that they are time reversal of each other. But this is probably not very. Yeah, it is somehow interesting. It means that we can split the group of time evolution into two semigroups, one for the past and one for the future, by choosing properly these spaces, but it is not quite interesting right now. I want to say something. Gamma states represents the exponentially decaying part of the resonance, which is essentially how the resonances behave during the most periods of time. To detect non-exponential decay is very difficult because it happens for very small times or very large times. Then gamma states are very good approximations for a spectral state for a unstable quantum state of resonance. But the point is the following: it looks like to be a pure state, but at the same time, we may think that something that decays in a sense may have. You see, pure states in quantum statistical mechanics have zero entropy. The point is this entropy can be defined for a gamma state, which is after all something which represents a serious decay. And the thing is, if gamma states were pure states, you have to forget the possibility to, it's not sense to define thermodynamic variables on the decaying state. I'm not going to speak about, but what I want is to justify the possibility of constructing thermodynamic variables like entropy, etc., in gamma states. And the point is that gamma states are not pure states, in spite of that they are represented by vectors. But always remember that these vectors do not belong to the Hilbert space, belong to a bigger space. They determine the entropy for a gamma state is not an easy task, and I have done it with the help of Osvaldo Chiviteresa from La Plata. But the point, what I want to underline is that gamma state is not pure state. How can I do this? The idea is a model that has been developed in principle in Brussels by Jonas Antonio, Dirwa Suhanecki, and Roberto Laura, and has been used largely by other scientists like Mario Castagnino, that many of us will remember him very much. But the point is that always the free Hamiltonian and the total Hamiltonian have some kind of spectral decomposition, and this spectral decomposition can be extended to some other types of observables. And the point here is just to define the states over this algebra of observables. I'm not doing, although I have written the details on the transparencies, if I go through the details, I will not finish on time. So that let me say simply that we can construct an algebra of observables and having several properties, like in an algebra with involution. And involution is but typically they are joint, and the algebra may have also an identity and some other properties. And there is a formulation which is rather old, of quantum mechanics based on algebras of observables, and which contains together with the observables, which are the self-adjoint, let's say, elements of this algebra, contain some other elements, of course, and in this formulation, the states are certain kind of functionals over the algebra. Functionals means that they are mappings that bring the algebras over the set of complex numbers. And we can, in this formulation, we can construct the general form for these observables, for these states, and well, this essentially depicted in this transparency. But what is important is that these functionals, for being in a state, had to have several properties, like positivity. This is defined here in red. The normalization, this functionals applied to the identity of the algebra must be 1, and some continuity properties. There are 3 properties that characterize in all algebraic theory what a state is. How many kinds of states are? There are essentially 3 types of states. There are pure states, mixtures, or mixed states, and then singular states. The pure states are mixture, we know all of them, because we know this from the elementary books in elementary textbooks in quantum mechanics. The singular states have been introduced many years ago by Van Hoff in order to describe states far away from the equilibrium. And one may think that gamma states must be singular states and not pure, neither pure nor mixtures. And this is exactly what happens. because one has to be if we have to define precisely what the gamma vectors are in this context. We have to define the functional of the gamma vectors in this context, and this is rather simple. We did with a group of Rosario many years ago, and the formal construction is given by this equation in red. So that the question is if they fulfill the properties of really properties of gamma state, or first of all the state, or then gamma state. And in fact, they are positive, they are normalized, and using certain topology for the algebra of observables or the algebra in general, this is discontinuous. We can define both. We can define the decaying and we can define the growing. They have several interesting properties, like for instance, when we apply the gamma state to any power of the total Hamiltonian, it gives the power of the energy that characterize the resonance. And the gamma state can be divided into two parts. One part was sometimes called singular, and sometimes called regular. The regular part does not change with time, but the singular time, in the case of decaying gamma state, changes exponentially, exactly as it should be. And analogous behavior happens with the growing gamma state. Therefore, the conclusion is that these two states in this formalism fulfill all the properties of gamma state, and we see that the consequences, the gamma states, must be classified among the singular states, exactly as the Van Hove states in systems far from equilibrium. And the last comment I want to make is just to comment a result that we obtained with a group of Buenos Aires, with Fede, with Sevi, with Marcelo, according to which we have proven interesting result that for any kind of any pair of observables belonging to these algebras, I mean, it happens that you take the commutator and you make the observables or the operators of the algebra evolved. It means that it happens that the limit when t is large, either in the past or in the future, gives 0, and but suggest the possibility of a quantum transition for large values of time is possible. And well, we have published this result in a couple of papers, and just simply wanted to mention it. So it is, Marcelo, it is exactly half an hour that I have spoken, right?
Yes, yes.
Therefore, I finish here, and I'm ready if you want to ask any question. I will escape from the full screen so that I can see you, because otherwise I can't see you.
Okay, thank you, Manolo, for your talk, for your interesting talk. Now we have time for questions. If you have any question, you can write on the chat, or you can say it.
Oh, I want to add that if you, I mean, you Marcelo, you Fede, you have my email, so that if somebody wants to discuss with me about any kind of point of this talk, I will be very glad to do it, so that you may, of course, ask me questions. Sorry, because I wanted to say many things, But after all, I realized that there are too many things cannot be said in just half an hour.
Okay. Well, Olympia has a question.
Olympia, listen to you.
Just a clarification, Manolo.
Yes.
You said that gamma vectors are not pure, but
yes.
you were not meaning that they are mixed states. They are singular.
No, not even singular.
But what is the relationship between being singular and having non-zero entropy?
No, well, the point is, you know that pure states have zero entropy.
Yeah.
And then in order to have, you may think that since the gamma vectors represent a very rapid changing quantum state, they must have some kind of entropy. But on the other hand, you represent them as a state vector. It looks like that they should have zero entropy. But the point is, it is a vector which does not belong to the Hilbert space. So that the point is, may I find another image, another representation of gamma states, so that they became evident that they are not pure states. And this is the formulation that probably you know, because Mario has worked very much with this, very much this formulation. So that and then once that it is evident that the gamma vectors are not, looks evident that they are not pure state, so that we can ask ourselves, can we calculate the entropy for a gamma state? And this is not easy. We can make some approximation, and the result is very funny. The result is very funny because the entropy looks to be complex. So that there is the real part and the imaginary part. The point is, what this imaginary part means? We only can conjecture the meaning of this imaginary part, which will be the interaction between the gamma state, which in the case exponentially, with the environment. This is the best answer we can give to the meaning of this. But Olympia, we may think about this, because this could be an interesting point to discuss.
It's a very interesting point, a very interesting, question, why, what's the relationship between the decay of gamma vectors? We don't need to make the gamma vectors to decay. We only need that the expectation values of gamma vectors decay. So
careful with expectation values, because as we know, the expectation values may not be well defined. We have to be careful with the idea of expectation value considering gamma states. That's a very, 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 very tricky point. Very tricky point. So that, and this is because, let me, if I can, wait a minute. Let me see if we can come back to the screen where I have. I have written this somewhere. But now I cannot find it. No, it cannot be over here. Let's see. Here, in this transparency, at the end you say the term. Some kind of a scalar product between the decaying and the growing gamma vector may be defined, and it be equal to real number and normalized to 1. However, if you write the same, decay and growing, this cannot be defined in general. And you can see in the physics model that this make no sense, because it's like to multiply two different distributions. And this is there are a structural difficulty in defining the mean value of the Hamiltonian or whatever in gamma vectors. It is nevertheless, I have a paper also with Osvaldo Chivitares and Roy Betan, in which we try to make a definition for the this mean value, but this is a very touchy point. We could, maybe Olympia. We have many discussions in the left, and we have to retake all of them. Olympia.
Olympia.
I came back now because I have it. Yes, a problem with the internet for a minute. So, but well, now I think that I begin to understand. But we can talk by email or by Zoom. It's very interesting. I had no clear at all that the expectation values were not well defined. Okay.
No, this is a very touchy question. But we have to. There are many subtleties that we may discuss.
Okay, and the point of entropy is one of them.
Yes.
Thank you.
You're welcome.
Well, any other question? Well, if there are no more questions, we thank again Manuel Cadela for his talk and for being present at this conference. And well, we continue. Thank you, Manolo. Well, we continue with the next speaker. The next speaker is Tim Mullin from New York University. Please, Tim, you can share your screen.
Please, Manolo, stop.
I have to wait for the other one to.
Okay.
Stop. Okay.
Well, the next speaker is Tim Mullin from New York University, who is going to talk about the emergence of Euclidean and Minkowski structure from discrete space-time.
Okay.
This Tim, when you want, you can start.
Okay. Everybody can see that?
Yes. Thank you, Tim.
Okay. Well, I don't have much time. This is all results that I've figured out in the last month, and this is the first time I'm presenting them. So I don't know quite how long this is going to take. I'll try and go quickly. Everything is conceptually kind of really trivial. The results to me were a little bit astonishing. Okay, so I've been playing around with, for some years, trying to think about how to do space-time geometry with a discrete foundation rather than a continuum. And so this is some recent results. So here are some things just to kind of contextualize this or motivate it a bit. So we start, of course, when we learn physics, we start with classical physics, Newtonian mechanics. I'm including special and general relativity as, you know, the kind of ultimate flourishing of a classical picture. But we know that all of that is wrong, right, at some level. All of Newtonian mechanics, right, Newtonian mechanics is not on the correct physical foundations. Maxwellian Electrodynamics is not on correct physical foundations. General relativity, it's a little bit harder to know exactly what has to give. We know that something's going to have to give in putting together a theory of gravity with the rest of quantum mechanics. You know, the failure in a certain sense of classical physics is kind of radical. the stability, that matter is stable, can't be obviously recovered from a Maxwellian picture of electromagnetic interactions. But right now, I just want to point to two actual physical phenomena that we know we need to account for. And one is the Aharanov-Balm effect, which doesn't have any natural understanding in terms of a classical picture of electromagnetics. It somehow has been taken to suggest, and I think this is correct, although you have to be careful about what it means, that the fields, the electromagnetic fields, are not really physically fundamental. Something else is. And then the big one, of course, is violations of Bell's inequality for experiments done at space-like separation. We know that you can't get that out of classical electromagnetic theory or general relativity or special relativity because they're local theories and they just won't allow for those phenomena. So we have to do something. Now, how do we deal with the non-locality? And this is actually also having to do with Aharanov-Balm, although I won't go into that now. How do we deal with that? How do we actually make that tractable in a mathematically clear way? Well, there's an obvious way to do it, a kind of very simple-minded way to do it, which is just to add a preferred foliation to the space-time. That would give us the resources to define various sorts of instantaneous physical connections between space-like separated events, where instantaneous is defined in terms of this preferred foliation. And if we do that, then we, of course, we just have this preferred foliation and we do the fundamental dynamics in terms of things succeeding states in this foliation, then we have no problems about causal loops or temporal paradoxes or anything like that, right? Because everything, all the temporal structure is going to be kept straight and straightforward by this foliation. Now, one way that you can do this, which is, you could say, the cheap way, is just to add the foliation in. That is, you start with a standard Lorentzian kind of metric that you'd get out of general relativity, and throw a metric on top, throw a foliation on top of it, and use that foliation in the course of formulating your dynamical laws. They're kind of easy to do a Bohmian kind of theory in that setting. It's kind of easy to do a GRW-like theory in that setting, where you make use of the foliation in a very straightforward way. But just throwing a foliation down on otherwise arbitrary Lorentzian structure seems kind of brute force and a bit unmotivated. So one thing I've been looking at is something that is much more radical, but much less arbitrary. That is, I'm going to start from a new foundation where this foliation is naturally going to be there from the beginning. Okay. And so what's the conceptual basis? Well, the other thing that I wanted to do is to reject the relativist account of space-time at the very first step. That is, you do not start with a four-dimensional differentiable manifold. You don't start with a continuum. You start with a discrete structure, right? You start with a discrete geometry. Now, if you do that, and again, I could argue this, but kind of easy to see that it's actually now going to be very hard to avoid there being a preferred foliation. Certainly, if you have a discrete underpinning like this, you can't have anything like a continuous symmetry, like symmetry under Lorentz boosts. And more or less, because each geometrical object has immediately neighboring adjacent objects, those adjacency relations are going to tend to pick out a preferred foliation automatically. Okay, so where do we hope might come from this? Well, obviously, I'm rejecting any kind of classical or relativistic picture of space-time at a foundational level, but the tremendous empirical success of classical physics and the tremendous empirical success of relativity, both special and general, means that you would need to explain why theories based on a continuum or based on a four-dimensional manifold with a Lorentz metric, why do they do so well, right? Why are they so empirically successful, given that I'm saying at a fundamental level, they're wrong? Now, we've done this before, right? It means somehow showing that something like the relativistic structure that we use emerges in a natural way from this quite different foundation, and emerges usually by some kind of statistical considerations of coarse graining or something like that, right? Now, we know that this kind of thing can happen. You might say, isn't it surprising that an emergent physics can be so very different in its character from the underlying physics from which it emerges? But we know that happens, right? Because we know that in some sense, Newtonian mechanics approximately emerges from quantum mechanics. We know that Newtonian gravitational theory in some sense approximately emerges from the general theory of relativity. And in each of those cases, the underlying theory is of quite a different character than the one that emerges, but you think you have a perfectly good understanding at the end of the day, from the perspective of the underlying theory, why these other theories that were actually quite wrong, nonetheless, were very empirically successful. Okay, so that's the kind of prologue. Let me just get down into the nitty-gritty details, because that's what most of this talk is. So I'm going to start, let me just start with spatial structure. We're going to put in time a little later, but the point is that both of these starting points are pretty much as non-relativistic as you can possibly imagine, okay? That is, I guarantee there's no attempt to make this look relativistic at a foundational level, and you might say just the opposite. What was the motivation? Well, the motivation was, let's see if we can do discrete geometry and do that in a kind of the simplest, most natural way and see what happens. And I can only give you my word that when I started developing this whole thing, I was not even vaguely considering what might emerge from it. I was just trying to write some stuff down that seemed to make sense. There are choice points when you do this, when you say, all right, what kind of discrete geometry am I going to use? I'll indicate some of those choice points. But the choices that I made are, again, pretty simple and pretty straightforward. They don't look arbitrary. They don't look, artificial, because they're really not. And from this foundation that is, as it were, completely non-relativistic in almost every sense, surprisingly to me, something very relativistic emerges naturally at a mathematical level. And that's what I want to go through. So how do we do discrete geometry? Again, all of this is just the way I do it. I didn't get this from anybody. I made all this stuff up. It'll all be completely unfamiliar to you, but it's very simple and straightforward. So if I have an n-dimensional space, and I want to think of it as fundamentally made of, as it were, geometrically atomic objects, I'm going to have different dimensional atomic objects. And so I just indicate these as n elements where n is the dimensionality. There'll be 0 elements, which you can think of as points, 1 elements, which are one-dimensional atomic objects. You can think of them as the little lines, 2 elements, which are surfaces, right? Atomic surfaces, 3 elements, which are atomic volumes. You could continue up. We have no need to go beyond 3 spatial dimensions. And these various elements are related to one another as bounded to boundary to bounded every one element has a pair of 0 elements as their boundary, for example. Okay, so you just would indicate the whole thing by incidence matrices that tells you which n elements bound which n plus 1 elements. That'll give you the whole structure. So the 0 elements bound the 1 elements, the 1 element, and every 1 element is bounded by a pair of 0 elements. That's just the relation between points and lines. Once you get up to 2 dimensions, the surface elements, the 2-dimensional ones, you have a choice. You have an infinite number of choices. One thing, so essentially you're asking, what's the shape of an atomic surface? Now there's a standard choice here made, which is to make them triangles, right? Because that's the simplest 2-dimensional polygon. And then when you go up to 3 dimensions to make the 3-dimensional things tetrahedra, because those are the simplest polyhedra. And that route, that particular choice of a path leads you to the theory of simplexes, which is probably pretty well known. My guess is many people have heard about simplexes one way or another. That's not the way I went. That's not the way we're going to go. If you go that other way, as far as I can tell, and I haven't looked in this in great detail, you won't get any of the results, anything like the results I'm going to show you. So I think this is actually quite an important decision, right? I'm not going to go points, lines, triangles, tetrahedra, okay? Well, what's the obvious thing, other thing to do? Well, make the 2 elements quadrilaterals, or if you will, squares that have not 3 but 4 bounding 1 elements, and make the volume elements prisms, or if you will, cubes that have 6 bounding 2 elements. And the scarecrows are there because, of course, I haven't done anything to introduce any notion of angle or distance here. This is all, as it were, at a purely topological level. So I can't literally say they're cubes or they're squares, but they are quadrilaterals or volume elements that have 6 quadrilaterals as their bounding surfaces. Good. So we're going to build it up that way, but just, you know, a small historical note, that's the way Euclid does it, right? So he says you start with a point. If you move a point, you get a line, right? That's your 1-dimensional element. If you move a line in an orthogonal direction, you get a rectangle. That's your 2-dimensional element. If you move a rectangle in an orthogonal direction, you know, you get a prism. That's your 3-dimensional element. So we're doing that instead of simplexes. And I'm going to depict them just using squares and cubic grids, because that's the easy thing to think about. But obviously, the actual angle relations and so on are not there. Good. So here's a prototypical 2-space, discrete 2-space. Each of the squares would be a 2-element. They're bounded. Each one is bounded by 4 1-elements, and each 1 element is bounded by a pair of 0 elements, which you can think of as the corners of the squares. And here's a prototypical discrete 3-space. We now have the three elements, which are the cubes, and they're bounded by the 2 elements and so on. So I take it everybody's following this. It's kind of trivial. It's not the only thing you could do, but it's a pretty straightforward, trivial thing to do. Good. First point, this is not Euclidean. If you treat these elements as atomic, which we're doing, so we don't think of the 1 elements as composed out of an infinite number of points. They're not. Right? They're bounded by a pair of points, but they don't have any points inside them. This is just not any kind of Euclidean geometry. If we wanted, there's a kind of metric that naturally comes along because it's discrete and we can count things. There's a kind of counting metric that comes along. And if you use that to define lengths and distances, then you get in the two-dimensional case, you get what's commonly referred to as taxicab geometry, right? So you just count how far is it from this point to this point. Well, you have all of these continuous paths that can take you from here to here, which go via connecting one elements, and you take the shortest such path and call that the distance, right? And if you do that, then the circles, I mean, the things you would define as circles just don't look circular, right? They look like squares. So the point C, what I've indicated on there are all of the points that are 3 units away from C in the taxicab geometry. You can go straight up or straight to the side, 3 units, or you can go over 2 and up 1, or up 1 and over 2, or, you know, and you get this thing that looks like a square. And if you did the same thing, centered it at point D, you would get another square. And the thing to notice is that those 2 squares meet each other and overlap along an entire side, right? They don't meet each other at a point. Whereas in a Euclidean geometry, if we were drawing circles, the first point where a circle centered at C could meet a circle centered at D, they would meet at a point, right? And then as they got larger, they would share a pair of points. So this is a non-Euclidean kind of structure, even at a topological level, even without bringing in metrical information in a certain way. This is very non-Euclidean. Obviously, it has preferred directionality in it, which a Euclidean 2-space does not have, right? You have kind of the vertical direction and the horizontal direction, and these are in a way completely different. Every one element is, as it were, either oriented this way or oriented this way, and you could define that in a perfectly rigorous way. Good. So I don't know of any sense, if you just looked at this discrete structure and its taxicab geometry, I don't know of any sense in which you would be inclined to say that anything Euclidean emerges, even if you go to very high scale, right? Even if you imagine kind of zooming out and having one of these grids with billions and billions of elements in it, the intrinsic geometry would still be non-Euclidean. The things, you know, even at large scale, the things that you would define as circles would still be, as it were, quadrilaterals, and they would meet along edges and things like that. So just going to larger scale, or just taking in any straightforward way statistical considerations, whatever that might mean, I at least don't see anything Euclidean emerging from this. Good. The preferred directionality also at large scale, even if you were far away and you, as it were, couldn't see the microscopic details, still it seems like these 2 directions would be preferred geometrically, and that maintains even at very high scale. It doesn't wash out. Good. So that's the spatial structure. So that's for 2 dimensions. For 3 dimensions, we would use a cubic grid. We want to make a space-time, so we want to add in some temporal structure. We want to add in time. And the whole point of a discrete geometry is that there is an adjacency relation, right? You can ask of any point, what are the immediately neighboring points, meaning points that are the other boundary of a single line, right? It's a single one element. Those are the nearest ones, and then the next nearest ones, and so on. Similarly, you can say that two elements, 2 of these surface elements are adjacent to each other if they have a common one element as a boundary, right? So there is a kind of adjacency relation which just doesn't exist in a continuum. In a continuum, no point is next to another point. No surface is, you know, I mean, certainly no point is next to another point. You could have 2 surfaces that share a boundary. So we're going to do the same thing with time. We're going to make it discrete, which means for any event, there will be the immediately preceding ones and the immediately succeeding ones in time. And following that model, okay, we're going to introduce arrows, and the arrows are arrows, and they have a directionality because time has a directionality, connecting different layers of this spatial structure, so that by following the arrows, they'll take you from any n element to its immediate successors in time. Good. And therefore, it's already easy to see what we're building before we've done anything else. There's going to be an intrinsic foliation, right? Because we're going to build up the space-time in these layers. We're going to take a spatial layer, put another spatial layer above it, and draw arrows one way or another from the one below to the next one, and then from that one to the next one, and from that one to the next one, and so on. And so again, at a foundational level, this is as non-relativistic as you could imagine. It has a foliation built into it from the beginning, not added arbitrarily to something else, all right? And the only question really left to us, if we've settled on the spatial structure of each of these layers, is how do we run these connections, these temporal connections between one layer and the next one? And here, again, there are different choices you could make. I'm going to talk about 3 of them. And I'm going to do this for the 2 spaces because they're easier to draw, but everything sort of goes through the same way for the 3 spaces. How am I doing? Okay, I'm halfway through. All right, so you can sort of think, take a layer, put another layer directly above it, and draw arrows up, only up to the immediate ones above, and you get something that would correspond to absolute Newtonian discrete space-time. Why? Because Newton thought of absolute space as persisting through time. So each spatial point identically remains through time and can be re-identified at later times. And that unique relation would be indicated by having only a single arrow here from each point to the succeeding point, to the succeeding point, to the succeeding point. Now that, however, that structure would be a complete disaster physically if we want to use this the way I want to use it. What do I mean? I mean, first of all, this would support a notion of absolute rest as there is in Newtonian absolute space. An object would remain at absolute rest if it always stays in the same, as it were, the same persisting point of space. Yeah. But the problem is, what I want to do is use these arrows to give me continuous paths through space-time, continuous temporal paths. That is, the paths that, say, a particle could follow. And if I only have these vertical paths, it means nothing can move, right? The points of space can't move, but also particles couldn't move either. The only place they could go at the next temporal moment would be directly above, and everything would be frozen. Okay. So everything would have, you not only have a notion of absolute rest, but everything would have to remain at absolute rest. So that would be a disaster. All right, so that's one thing we could do, bad idea. We could go the other direction and say, look, let's connect up every n element on one layer with every n element on the next one, right? So there's no preferred relation at all between the spatial elements at one moment and the spatial elements at another. That, of course, gets extremely messy. I didn't even draw them all in, but you get the idea. Okay, this would be sort of corresponding to what we think of as a Galilean space-time, where there is no preferred relationship between an event at one time and any event at any other time. But that's equally a disaster, because now there's no restriction on these, what you count as a continuous temporal path. Sort of any selection of any n element, you know, say point from every one of the layers will count as a continuous path, because there'll be an arrow that goes from this one to that one, then to this one, then to that one, okay? So you kind of lose any interesting space-time structure at all. That's a bad idea. So what's the solution? Well, one doesn't work and infinitely many don't work. So let's just look at finitely many. And there are different ways that you could do that. And instead of trying to walk you through them, I'm just going to go to the one that turns out to give you really nice results. So this is what I call a simple discrete three-dimensional space-time. We're not going to have any absolute rest at the fundamental level because each zero element, right, for example, or two element, has four immediate temporal successors. So from this point, I can immediately go at the next layer to four different points, none of which counts any more than any of the others as staying in the same place, right? And the key to this is you don't stack the layers vertically above each other, but you displace them so that, as it were in this diagram, directly above a point in this layer will be the center of a square on the next layer, okay? So you displace them from each other in that way. And then you go back and above that, you're then back to the original. So and then you put arrows from each point to the four corners of the square above it. Yeah, it's easier to understand by seeing it. So there's what this thing looks like. And maybe it's even easier to see it from above. If you kind of look down on it, you would see that we have this one square grid, and then the second square grid with the solid points is displaced from it so that the points in the original grid fall at the centers of the squares of the next layer up. And then you put four arrows going out, as it were, northeast, northwest, southeast, and southwest. So there are four ways you can go. Good. Now, there will now be, you obviously do not have, if particles could follow these arrows, they're not now stuck the way they were originally and can only go up. And there's a kind of light cone structure. So there's something that looks a little bit relativistic here, because from this point, there are only 4 points I can get to in the next layer, and then a limited number I can get to in the next. And I mean, the thing becomes larger as you go up. So there's something that kind of looks like a light cone. There's no state of absolute rest because, one way to think about this is like the fundamental connections are all light-like. They're all null. And from any point, there are 4 ways you can go. And so there, you can't stay at rest, right? If a particle had to do that, if a particle wanted to, as it were, try to go straight up this diagram, it could only do it by something we might think of as Zitterbewegung, right? It's got to be kind of oscillating around as it goes up. There is a kind of emergent notion of absolute rest here, because if I take not this layer and the one right above it, but the one above that, then a point here will be preferentially related to a particular point 2 layers up by there being the maximum number of connections to it, right? So if I go from here to the one, as it were, straight above it, there are 4 ways I can get there. I can go this way, that way, that way, that way. I can get to other points up here, but there are fewer routes, right? So if I ask, which point above this one is maximally connected to it by continuous paths, that does pick out something like an emergent state that you could call absolute rest. So again, you might say extremely non-relativistic. And the other thing that's still non-relativistic here is if we call the light cone, if I take any event, any zero element, and I just follow the arrows and see where could you get from there, I get this growing structure, but it's a square-based pyramid, right? It doesn't look like a cone, right? It just looks like a bigger and bigger pyramid. And if I take a horizontal cross section through it, those will be squares. So just as with the taxicab geometry, I don't seem to have anything that looks at all relativistic. Okay, so again, it's seen from above. I mean, so if I started at some point, you can go out to the next 4 points, and if I cut through that, I get a square. And then if you think of all the places I could go from those 4 points, those are going to make a bigger square and a bigger square and a bigger square. Good. So where are we now? I'm sorry, I'm rushing so fast, but I know I don't have much time. So we have a discrete space-time has a light cone structure, otherwise has a completely different character than Minkowski space-time in many different ways. There's a preferred foliation. Spatial geometry has preferred directions in it. There's an emergent state of absolute rest. None of this occurs in Minkowski space-time. And they retain at arbitrarily large scales. They don't in any obvious sense wash out just because you go to high scales. However, and this is kind of a shock, something very close to a Minkowski structure naturally emerges. How is that? Well, let's think about degrees of temporal connectability. I already did that when I talked about this emergent state of absolute rest. I said, from this point, what point above it has the most distinct paths that lead to it, right? So I can count, because this is all discrete. I can just count these paths. And so between any pair of these one elements, I can count the number of distinct continuous temporal paths that will take you from there to there. Could be 0, then we'd say they're space-like separated. That count is directly connected mathematically to Pascal's triangle and the binomial distribution in ways that are probably familiar if you think about it. But the key here is that you don't actually use Pascal's triangle, but you use this thing, Pascal's square-based pyramid, which is something I only learned about in the last couple months, but it's very simple. It's like Pascal's triangle, except taken up to 3 dimensions. So here's Pascal's square-based pyramid. Imagine stacking cubes up like this in a kind of ziggurat. And then again, just like with Pascal's triangle, put a 1 in the top, and then in every lower layer, just add the numbers that connect to it. So the next ones down all get a 1, and then the next layer down, you get 1s in the corners, and then 2s, and then a 4 in the middle. That's again, the middle one there has the most connections. And it's easy to see you're, again, just counting distinct paths that you could take through this structure from the top down to any of these parts, okay? So that's Pascal's square-based pyramid. There's a Pascal's triangular-based pyramid, which does different things. We're not using that. We're using this stuff.
Yeah, sorry.
If we cut through this at, say, the 5th level, here are the numbers that you would get. And so these would be, again, the number of distinct continuous paths from that top down to any of these cells. And you notice 2 things. There are really 3 important features that this set of numbers have. I'll just mention what they are, and then you can go back and look and see that they're there. The first feature is that if we look along each edge, we just get the numbers from Pascal's triangle. That is, we get the normal binomial distribution. So 1, 4, 6, 4, 1 along the edges. The second really important fact is that in the interior.
Sorry, Tim, you have already reached the 30 minutes. You can continue using the time for question if you want.
Yeah, I have to. I mean, I'm just getting to the payoff. Okay.
Okay.
I'm sorry, but I've never done this before. Okay. The interior you get by a multiplication table. Okay. So you'll notice all the numbers in the middle are just the product of the corresponding numbers along the edges. Yeah. And that you can prove is always true. And then the third fact we're going to use is that as these numbers get large, we know the binomial distribution is well approximated by the Gaussian, which we have there. Okay. Now that's just an approximation. It only kicks in when the numbers get large and you have to stay away from the tails and stuff like that. It's a good approximation. So let's use those 3 facts. So if we introduce coordinates along the edges so that the center of the edge is 0 of the x-axis, right? The center of the edge is the 0 of the y-axis. Then we get the interior numbers by multiplying together these 2 Gaussians. This is going to be a good approximation. And if you just look at the final result there, it means the degree of connectability, you'll notice, goes as e to the minus 2 over sigma squared, x squared plus y squared. That means any cells, if we now number these cells by integers, which is what we're doing, any pair of cells on a given layer where x squared plus y squared are about the same number have the same degree of connectability, right? They have about the same degree of temporal connectability to the top. So in a very strict sense, a circular kind of structure emerges as loci of equal temporal connectability to the top, right? And that emerges in a pretty strict sense, although you do have to stay away from the tails. You don't get too close to the edges. It emerges in those conditions where the Gaussian is a good approximation to the binomial distribution. So that's part of what we wanted to do. All right, those are my caveats. Here's some actual numbers, right? If we go up to the 1000th level and we compare the connectability of these 2 points, 200, 0 and 141, 141, you'll see the connectabilities are almost exactly the same. And if we square those and add them, those numbers are almost exactly the same, right? So if we just look at loci of almost the same connectability, they look more and more like circles. What if we cut vertically and look over time to loci of vertical cross sections? Well, we know in Minkowski geometry, if we take a cross section like that and we look for points of equal proper time from the origin, that'll be a hyperbola, right? And the thing would be delta t squared minus delta x squared equals a constant. What if we cut through Pascal's pyramid? Well, the solid line, that's our hyperbola. That's what we're aiming at. And these lines at the top are regions of approximately the same connectivity through time. This is using Stirling's formula for an approximation. So if you just look at that hyperbola and you look at these things above, that looks really, really close. Let me just give you an exact calculation. Let's suppose we know that a hyperbola is fixed. Once we have the symmetry, it's fixed by 2 data points. So I'm going to give you 2 data points, so I'm going to go up to the 800 level. I'm sorry I'm doing this so quickly, but this is the last thing I'm doing. Go up to the 800th level, right? And look at the central point. We can exactly calculate the degree of connectability. It's this 3.5 times 10 to the 478. Okay, that's at the center. Now go up 10 levels, go up to the 810th layer and look for the point that has the nearest degree of connectability. That turns along what we can think of as the x-axis. That turns out to be 75 cells along off to the side. And there's the calculation. You'll see it's almost exactly the same connectability. So now I have 2 points. Now I'm going to fit those to a hyperbola, which, the best fit is this number here that I'm giving you. And I'm going to use that hyperbola to make a prediction for 1,000 layers, right? To go up another 190 layers. And so if I use the hyperbola, the prediction would be 354.60, which we need to round it to an integer. So we'll round it to 355. And now let's do the exact calculation. Again, something times 10 to the 478th. So this hyperbola is a really good approximation that's giving you equal degrees of temporal connectability in this discrete structure. Now, in a 4-dimensional space-time, we do the same thing. We just use cubes, and now I'm at my conclusion. So what's the conclusion? Even though the foundation is profoundly non-relativistic in every possible way, right? Within restricted bounds where these approximations like the Gaussian are good, we get something very close to a Minkowskian structure as a purely mathematical fact. Now, in order for that to have physical significance, we would need the physical laws to be sensitive to degrees of temporal connectability, which is just counting the number of different paths through this structure. And my last comment is, one approach to understanding quantum theory is sum over paths, right, which was pushed by Feynman, which at least gives you a suggestion that looking at temporal connectability via paths is not a physically irrelevant thing to be looking at. And now I'm done.
Well, thanks, Tim, for your talk. We have time for a question. Anyone have a question? Okay, Elias, you can ask.
Hi, Tim. Thanks for the talks. Really, really nice. Yeah, actually, my question was it's related to the last things that you mentioned about this connectivity. I mean, one would have thought that that you would need to relate proper time, like in the analogy, proper time to the length of the path, right? Like
Right.
how many steps you need to take. But instead, you need to use this connectivity, which is related to the number of ways you can.
That's right.
So I don't know if there's anything else you can say about it. And I mean, I think it is counterintuitive.
Hey, look, I agree. I mean, you know, there are 2 points here. There's a purely mathematical fact that the damn count of connectivity does what you want it to do. And then you're absolutely right. What I need is now a physics where degree of connectivity matters.
Yeah.
Right. Where now, of course, counting is not a particularly good idea because we know that, as it were, proper time acts oppositely than the way a Riemannian distance does, right? We know as we go out to the light cone, it goes to 0. We know it does the anti, you know, if you do counting, then you would expect the triangle inequality, and we get an anti-triangle inequality. So, you know, the counting idea never was right.
Yeah.
But whether you know, how to bring connectivity in, you're absolutely right. This is the remaining piece. My only point is that in a sum overs paths kind of approach, you might imagine that points with equal degrees of connectivity have physically interesting shared characteristics, depending upon the rules of how things propagate here. Right? I mean, the basic picture is that is of course nothing naturally wants to go. As I said, it's something going straight up is going to be jiggling a lot, right? It's like Zitterbewegung. And it's sort of, as it goes off to the side, it kind of jiggles less. I mean, so you need to think, you might think in a kind of Bohmian setting where what you're doing is doing a kind of pilot wave. And all of these paths are interfering with each other, that equal degrees of connectivity would give you equal sorts of interference phenomena or something like that. That's very vague, but you're right. That's exactly what would be left.
Yeah, no, it's suggestive. I agree. Very nice. Thanks.
Well, we thank Tim for your talk. And now we have finished the first part of this session. We are going to have a 10 minutes break, and we return at 15:30. Thanks all for the participations.
Well, Tim, are you still there?
Yeah, I'm here.
Yeah, I want to ask you a question because
Sure.
I know it's because have you tried on obtaining some curvature in space-time, like some approximation to general relativity or something like that?
I mean, look, the interesting thing about this is that if you think about what I was saying emerge when I said these circles, kind of circular things emerge, yeah, they only emerge away from the edges. As you get, you know, the sort of actual light cone structure has this square-based pyramidal structure, and as you approach those edges, the connectivity doesn't do what you want at all, and that's exactly where this Gaussian approximation breaks down. So the circles kind of emerge in toward the center. So the story here would be that, say, light, if you want light to really produce something that looks like light cones, they're not going out along the edges. They're somehow in the interior. Now, if they're in the interior, then even if the bounding light cone is fixed, you could imagine effects that would shift, you know, narrow or widen or distort the effective light cone, staying within those bounds. And that could give you similar effects to curvature, right? So it would amount to an approach like when they approach general relativity by having a flat background and then doing deviations off the flat background. Yeah. That I think is probably more the way you would go than literally trying to get curvature into the geometry. You'd kind of get the curvature, you'd have this fixed geometry, which is really only defined at a kind of topological level. And that doesn't change at all. What changes is how things propagate through it. And then again, what you'd like to do is show that that approximately gives you the same results in terms of changing light cones and narrowing them and whatever that you would get out of general relativity.
I see. Thanks. Very interesting.
Can I ask something else related to this question?
Sure.
And what about changing the rules for combining three elements to form these three structures? So couldn't you introduce some sort of curvature or something related?
You know, you're welcome to try.
Yeah,
all I can say is
I can see that there are like an infinite number of options.
Of course, I mean, one thing is there are an infinite number of ways to do this.
Yeah.
And it took me a long time to settle between triangles and squares, to tell you the truth, right? I did that a long time ago, but I had to struggle with that. Obviously, and when it comes to adding these arrows in, there are other things you could do, right? You could add in fewer, you could add in more.
Sure.
So, you know, all power to you if you want to explore the possibilities. What I kind of tried to do, I think, is do pretty much the simplest thing that didn't immediately collapse into nonsense. And amazingly, out of that falls into my lap something I'd not even been aiming at, right?
Yeah.
Which is something that looks very
nice,
Minkowskian. And I'm just kind of astounded by it. Now, you know, maybe it's just a coincidence, but it seems a kind of pregnant thing, right?
This is astonishing, the result. My question is this: if you are thinking about defining the points, the very bottom, at the very bottom level, in terms of something like events and interactions at the quantum level, perhaps this may be at the non-relativistic quantum level. I mean, very non-relativistic framework, but it's something to give some physical content to points from the very, very bottom. Perhaps it can be interesting. I don't know if you are thinking about that.
I mean, what I'm doing right now, I mean, there are two things to say here. One is, as I say, a kind of one obvious way to bring quantum theory into this is a kind of Bohmian picture where this is the underlying space-time geometry. You have point particles that are traveling along continuous trajectories in it. And then the quantum part comes in the guiding equation, right? And you need that, and the dynamics of the wave function is related to this connectivity stuff, which is exactly what this kind of Feynman path integral formalism at least suggests, right? So then the real physical stuff is just kind of point particles moving around in a discrete space-time. The other thing you can try to do, which I'm working on now, is to put something like Maxwellian electrodynamics, which turns out to be really interesting. It turns out the natural way to do that, and this is connected to this Aharanov Balm stuff, is first, it's not even that what's really physically real are the vector and scalar potentials, but what's physically real is something that lies underneath even those. Okay, so there's this it's what I call a two-field U, single two-field, and it gives rise to the vector potential necessarily in Coulomb gauge. And of course, in Coulomb gauge, the vector potential changes instantaneously, right? So again, you get resources for non-locality. And this is just looking at Maxwellian electrodynamics.
Okay.
You know, how you quantize all that, I have no idea.
Okay. Thanks.
No.
Okay.
Are you there?
Well, we are on time. Now we continue with the last two talks of the days. The next speaker is Ana Maxwellian from University of Córdoba, and she's going to talk about entropic characterization of quantum state with maximal evolution under given energy constraints. Please, Anna, when you want, you can start sharing the screen.
Hi, thank you. I will share my screen. So if you see little lines on my face, don't worry, it's just that my camera is broken. There are no bugs here around. So can you see my screen now?
Yes.
Okay. So, yes, thank you, Marcelo. I want to thank the organizer for inviting me to give this talk at this night conference. This is one of my favorite conferences where we can meet with friends and discuss in a pleasant atmosphere. I would also like to thank the organization of this edition of the event in this context of pandemic, and I hope that we can meet in a face-to-face meeting next time. I'm going to talk on an entropic characterization of quantum state with maximal evolution. This work was done in collaboration with Andrea Valdez Hernandez, Cesar Maglione, and Angel Plastino. And to begin with, I will try to motivate the introduction of a measure of the amount of evolution, which is the measure that we maximize in order to obtain these optimal states. There are several questions one can ask when analyzing the limitation associated with quantum evolution. An important question is, for how long does one have to wait in order to see something happening? And another question, which is related to this question, is how fast can a quantum system evolve to an orthogonal state? And this is the basic question addressed by studies on the quantum speed limit. Our alternative and complementary question is how much happened during a certain period of time. This second question is the question I will address in this talk, but let me first comment briefly some ideas behind the quantum speed limit. The problem of optimal evolution has attracted a lot of interest. That is because besides intrinsic interest as a fundamental question, the time limitation associated with quantum evolution also have practical implications. Several work focus on the limits imposed by the basic laws of quantum mechanics in the speed of information processing and information transmission. This is the basic scheme. We have here the initial state, psi 0, which evolves unitarily to an orthogonal state in a time tau. This is the orthogonality time, and this time can be regarded in the context of quantum computation in the computational state needed to perform some quantum process. This orthogonality time is connected with several fundamental aspects of quantum physics with important quantum implications in the field of quantum information. And the concept of distinguishability, because it's the time to evolve from between two distinguishable states, the concept of distinguishability appears here, and this concept will have a central role in the talk. So the first answer to this first question, came with this work in 1945. The work was by Leonid Mandelstam, who died before the article was published, and his student Igor Time. They derive a kind of uncertainty relation between energy and time, and that bound the time of the speed of evolution in terms of the spread of energy. Several years later, indeed 53 years later, a second answer came with this work by Norman Margolis and Lev Levitin. They derive another bound which is independent from the Mandelstam bound, in the sense that the Mandelstam bound cannot be reobtained in terms of this other bound, and they bound the speed of evolution in terms of the mean energy of the system relative to the ground state. So the Mandelstam time limit was introduced, as I said before, as an uncertainty relation between energy and time. And even if it is not crucial for this talk, I prefer to distinguish here between bounds and uncertainty relations. Also for completeness, I want to mention this work, also in the 90s by Anandan and Aharanov. They rederived the Mandelstam time limits on geometric foundations. And according to this work by Anandan and Aharanov, the Mandelstam time limit can be interpreted as a comparison between the path followed in the state space with the geodesic endpoint of that evolution. Here are the two bounds. And more recently, in 2009, Levitin and Toffoli introduced a unified version of the bound that take this form, and this bound is tight, and this expression is one usually used in problems in this field. So to address the second question, I will try to explain why we think this is an interesting question and even more unnecessary question to be answered. So when studying problems related to the speed of quantum evolution as measured by the orthogonality time in systems evolving continuously in time, there are at least two points or two observations that we need to bear in mind. One is that most of the initial state never evolve into an orthogonal state. In fact, the subset of the initial state that do evolve into an orthogonal state is a subset of measure 0 in the state of all space. And even for those states that do evolve to an orthogonal state, the number of times that the system reaches a state orthogonal to the initial one in an interval of finite duration is itself finite. So from these two observations, we can conclude that tau, the Biot's grid conceptual value, is not directly applicable in many relevant physical situations. So an alternative procedure, because this tau cannot be used to characterize the speed of evolution of many states, because, for example, this time is infinite for many states and then cannot be used to characterize the speed of evolution. As an alternative procedure, one can study the time needed to reach a state having a different value of the overlap, that is not the time to reach an orthogonal state, but the time to reach a state with a given different from 0 value of the overlap. But in contrast with the decay of 0 overlap, there are not mathematical or physical reasons to choose one value of the overlap as a more fundamental than another. So it's very difficult here to put some conditions, and maybe it makes sense to explore different possible values. An approach that takes into account different possible values of the overlap. And that is what I'm going to tell you in this talk. So this is the outline of the talk. I first will introduce the amount of quantum of evolution. I will discuss some properties of this measure, and I will show the behavior of the measure for some typical simple quantum systems. Then I will show you a relation of this measure with the timeless approach to quantum dynamics. And through an entropic approach, we will see the quantum system that optimizes the quantum evolution under constraint given by a fixed mean energy. And to finish, I will present some discussion and final remarks. So the notion of distinguishability between quantum states is of particular importance in quantum information and in quantum computation. In this is this concept of distinguishability, which leads to the idea of a kind of orthogonality. And this distinguishability can be quantified between two pure states with the square overlap of the state. If the square overlap, the square modulus of the overlap of the state is equal to 0, then the two states are perfectly distinguishable. This corresponds to two orthogonal states. And on the other extreme situation, if the square modulus of the overlap is equal to 1, the two states are totally indistinguishable from each other. That is, indeed, that these states represent the same physical state of the system. So our approach is based in the idea that a pure state takes different degrees of distinguishability. And in short, we propose a measure which is a complement to the time to orthogonality and to the time associated to the number of computational steps, to use a measure of the amount of the evolution of a system given by the average distinguishability of the system as the system states, as the system evolves. So we define a measure in terms of the average of the time average distinguishability of the system. So this is the quantity that we propose to quantify the amount of quantum evolution. This quantity is defined in an interval T1, T2 of length capital T. And here, phi t and phi t prime represent two states of the system at different instants of time, t and t prime respectively. And this average distinguishability provides a quantitative assessment of how diverse are the states that the system visits during this time interval. So high values of t, that is values close to 1, means that these two states are highly distinguishable or can be perfectly distinguishable. And on the other hand, low values of d, close to 0, means that means a low variation between the state of the system at time t and at time t prime. That is, this overlap is close to 1, and then this measure is close to 0. So if we now consider this measure and move the interval of time, that is, we consider the measure d in the interval t1 plus delta and t2 plus delta, we reobtain, with some algebra that I don't show you here, we reobtain the same measure. So this measure d depends on the interval only through the length of the interval. So we can write the measure in this more simple way. This capital T is the length of the interval, and without loss of generality, we can write this integral between 0 and t. So this measure d does not depend on which time window we are looking at, but only the size of the window. So this has a time translational symmetry. And this is a nice property of the measure. So now to go deeper in the form of the measure, which we do is to write this state phi t in an appropriate configuration space basis x. We can represent this state in this way, where here x represents some spatial coordinate or any other degree of freedom of the state. And this is the wave function which satisfies, as usual, the Schrödinger equation. And it can be expanded in terms of the orthonormal eigenfunction and the eigenvalues of this Hamiltonian H here. And this coefficient satisfies a normalization condition as usual. If you put all together, this expression here and this expression here, we can compute this amount of evolution with the Dix form. And we can integrate, and we obtain this final expression from the amount of evolution that experiences a system in a time interval of length capital T. Where here we define this omega nm as the difference between two different energies, En and Em. So this expression has two contributions. One here, this first term, which only depends on the coefficient of the expansion, that is only depend on the initial state. And this other contribution, which is an oscillatory term, which depend on the length of the interval. So we can define an asymptotic limit for this measure, which is the limit of this measure when this capital T goes to infinity, We call this asymptotic value DL, and we can prove that this measure is always less than or equal to its asymptotic value. And I will show you now with some examples because it's more, easy. Some illustrative examples, the behavior of the measure in terms of this time, t, and how the measure quickly reaches its asymptotic value. So we compare the time scale associated with the measure d with other relevant time scale of the system. For instance, the dynamical of the system characterized by the behavior of the autocorrelation function. So this is the autocorrelation function. It is defined as this overlap. And we compute here both functions, the autocorrelation function and the amount of evolution for a qubit system. So here we have this two-level system, right in terms of this orthogonal eigenfunction phi1 and phi0, with two eigenvalues, E0 and E1, and with this coefficient A0 and E1, which satisfies the normalization condition. So we can compute the autocorrelation function and the amount of evolution, and we see here that the amount of evolution quickly reaches. These figures are in terms as a function of the capital T over Tc, where Tc is the natural period of the system. And we see that the amount of evolution quickly reaches in all cases. These different cases correspond to different values of this coefficient A0 here. And in all cases, the asymptotic value is represented by this dashed line here. So in a time which is close to the characteristic time of the system, we can see that the measure reaches the asymptotic value for all cases. So we also consider an harmonic oscillator, showing that in a period of the autocorrelation function, the amount of evolution again reaches its asymptotic value. Here we have a t-level system. We consider different values of t equal 4, 8, and 50. And we see that this measure d, we can show that this measure d is maximal in the equally weight case, that is when all the coefficients of the expansion are equal to 1 over square d, where d is the number of levels of the system, and that the measure increases with the number of turns with the number of the turn in the expansion, or which is the same as the information regarding the particular energy eigenstate decreases. This curve corresponds to 4, 8, and 50 levels in the expansion. We also consider here a 2-qubit system, which is a 4-level system. Here we consider a degenerate spectrum of energy, and we obtain a similar result. The measure d reaches or almost reaches its asymptotic value in a time related to the characteristic time of the system. So to finish this part of the talk, we consider a wave packet in an infinite one-dimensional potential of length with width L. If the initial state has this form, is a Gaussian packet, we can analytically approximate the coefficient of the expansion, and we can compute the autocorrelation function and the amount of evolution for this packet in that infinite well. And although the analysis of the time scale involving this problem is more complicated or more elaborated than in the previous example, for our purpose, we show the behavior of the measure related to the classical period of the system, and we see that for a time close to the classical period of the system, the measure, the amount of evolution almost reaches its asymptotic value as in the previous examples. And I show you here this last figure, in which we can see that the system exhibits rich and interesting features in the dynamics, such as a revival. Here we have a revival of the system at a time scale which is larger than the time scale in which the measure of the amount of evolution reaches its asymptotic value. So we can safely state that with some relevant aspect of the dynamic of the system are happening, the measure of the amount of evolution is in its or almost is in its asymptotic value. And we will come back on these results for the last part of the talk. So I will show here a relation with the timeless approach to the quantum dynamics. The time problem is central to modern physics. It impacts quantum mechanics, cosmology, general relativity. We have in the afternoon session of yesterday some interesting talks about time, indeed about the timeless approach also. And in an attempt to incorporate time in a fully quantum context, Page and Guter proposed this timeless approach in 1993 in this work. And according to this approach or this proposal is based on three main assumptions. We will have a clock and a system, which is the rest of the universe, and the clocks and the system do not interact. The clock provides the parameter T to the system, and the system and the clock are entangled, and the clock and the system as a whole are in an eigenstate of the total Hamiltonian. So in this, according to this timeless approach, the evolution of the rest of the universe, which is the system we call R, reflects the fact that for different states of the clock, there correspond different states of the system of interest, which is all the rest of the universe. While the whole universe, which is this system R and the clock, remain in a single static state. So according to the timeless approach, both the dynamics and time emerge from the correlations between the clock and the system. So this is a scheme. I borrowed this figure for this nice recent paper. Here we have, in this timeline proposed, one considers the whole universe as a closed quantum system, composed by a clock, whose degrees of freedom will be denoted by T, and the rest of the universe, which we call R, with some coordinate X. And well, here there is a representation of the clock as a quantum system. Each of these subsystems, C and R, have its corresponding Hilbert space. And this whole system, the universe state, is in a eigenstate of a total Hamiltonian with corresponding eigenvalue equal to 0, consistently with the Wheeler-DeWitt equation. So we consider that this system is described by this function. We can write this expression for the state of the universe, where again here X represents a spatial coordinate or any other degree of freedom of interest of the system, or which can be of one or many particles, and T represent the base state of a clock, and this is the eigenstate of these are the eigenstate of a clock observable. So I don't go. I won't go deeper with these approaches, but one thing that one sometimes is interested in is in calculate the entanglement between the clock and the rest of the system. As the universe is in a pure closed quantum state, the entanglement can be quantified through the degree of mixedness of the marginal reduced density matrix. So which we do here is compute the reduced density matrix of the system of interest, which is the rest of the universe, tracing over the degrees of freedom of the clock, and we compute the entanglements using the linear entropy. Of course, we can compute the entanglement using the von Neumann entropy, which is the standard measure of entanglement for pure state. But this is also a nice quantifier of entanglement. And if we obtain this for the entanglement of the between the system and the clock, and if we compare this expression with the our expression of the amount of evolution, we can say that the amount of evolution experienced by a quantum system in a time interval capital T correspond from the time point of view to the amount of correlation between the system and the clock. And according which we use our previous results, which we see in the few slides before, as the length of the interval T increases, the quantum correlation between the clock and the system, it has the value dl, which is the asymptotic value of the amount of evolution. So just going into the last part, we assume that our measure D is well approximated by its asymptotic value. So we take D equal to its asymptotic value dl. And under this assumption, we now investigate the state that maximize this amount of evolution under constraint of fixed mean energy. So this is now our measure. This is the asymptotic value of the measure. Remember that here we are taking only the first term in the whole expression of the amount of evolution, because we are approximating the amount of evolution with its asymptotic value, because this asymptotic value is quickly reached in the dynamic. So this expression here can be written, because of the normalization condition that satisfies this coefficient, can be written in this way, which can be writing again in this way, now in terms of energy. And here we can identify this probability of getting the particular value of energy EI when measuring the system energy. So we can write this quantity here, or this GL, equal to the linear entropy of the energy distribution. And the linear entropy has a clear statistical interpretation. If one measures the energy of two identical prepared copies of the system, the linear entropy equals the probability of getting different results in these measurements. So in this sense, the linear entropy can be regarded as a measure of diversity in the way that the different energy eigenvalues are represented in the quantum state under consideration. In fact, the linear entropy is used as a diversity index in biology, for example, which is sometimes referred as a Gini-Simpson index. So if we think here in the situation of zero energy diversity, this situation corresponds to an energy eigenstate, which is when the system is in an energy eigenstate, and this is a state that basically that does not evolve. So we now investigate the state that optimize this measure, this linear entropy, and these are the steps that we follow. We approximated the amount of evolution by its asymptotic value, and the asymptotic value of the amount of evolution is equal to the linear entropy of the energy distribution. So we find the optimal state, and this optimal state can be regarded as the state that evolved the most under given energy resources, and have an energy distribution which is given by this expression. And this is a problem of optimization with two constraints, the normalization and the fixed mean energy, and can be usually solved using Lagrange multipliers. But we follow a different path, and we directly prove that this optimal probability distribution, that this is the optimal probability distribution of energy, where here A is a constant of normalization, a factor of normalization, and B is a real parameter with units of inverse of energy. And this is the Heaviside step function. And we proved that between all the probability distribution that satisfies the normalization condition and the fixed mean energy, this is the optimal probability distribution, which maximizes the linear entropy. And we, with this equation, we obtain this relation for the optimal amount of evolution, which resembles this thermodynamical relation between the standard entropy, the energy, and the temperature here. So we can identify that this 2AB plays the role of an inverse temperature-like quantity, and that this optimal measure of the amount of evolution satisfies a kind of thermostatistical relation as the thermodynamical relation, as that well-known thermodynamical relation between the entropy, energy, and beta associated with the canonical ensemble. So, of course, this problem also can be solved using Lagrange multiplier, and this is the variational problem that we need to solve. When here we have one Lagrange multipliers alpha, and the normalization condition, the fixed energy condition. And if we solve this variational problem, we obtain, of course, the same probability, optimal probability distribution. Here we obtain this expression, and we can relate alpha 0 with 2a and alpha 1 with 2ab. And with this method, the cutoff of the probability distribution need to be analyzed. It cannot be derived directly from the solution of the variational problem. So just let me show you the last result. We explore the behavior of this optimal measure of the amount of evolution as a function of the mean energy of the system. And these figures correspond to the examples we saw before, the qubit system, the harmonic oscillator, the 2-qubit system, and the Gaussian wave packet. And the detailed dependence of the measure differ from systems because they have different energy spectra. However, all exhibit a similar behavior. All the measures are the curve exhibiting a monotonally increasing behavior of as a function of the mean energy, which corresponds to a positive value of that temperature-like quantity. And the curve also exhibit a definite concavity, which means that the optimal amount of evolution and the energy resources obey a relation of diminishing returns. That is, as the mean energy of the system increases, further increments of the mean energy are less efficient to increment the optimal amount of evolution. And this is more evident in these two figures here on the left, where we can see that increasing the resources of the system, the optimal amount of evolution increase in a small quantity. So to finish, I will show you some discussion. We have introduced this quantitative measure of the amount of evolution. This measure is defined as the time average of the distinguishability between different state of the system at different instant of time in a given interval. We show that the measure depends on the interval only through the length of the interval, which is a kind of a translational invariant property. And we show that this measure is always, sorry, I did forget. This measure is always equal or less than its asymptotic value, and this asymptotic value is equal to the linear entropy of the energy probability distribution, and this asymptotic value is quickly reached in most of those typical quantum systems I show you. And using this approximation for the model of evolution, we investigate the quantum state that evolve the most under given energy resources. And we find that the relation between the optimal measure and the state is related to the mean energy through a thermostatistical light formulas. So that's, I think I will stop here. And
well, thanks, Anna, for your talk.
thank you for your attention.
Well, now we have
the work, the reference of the work.
Oh, perfect. Well, we have time for questions. We have a question for Martin Bosic. Martin.
Hi, Anna. Thanks for your nice talk. I have a question, a short question, maybe speculative. When you calculate the entanglement between the clock and the system by using the linear entropy, you recover a relation between this entanglement measure and your measure of average distinguishability. Okay. Well, what happens if you use another measure of entanglement? Because for pure state, or entropy are equally, no?
Yes.
You can define another well-defined measure of average distinguishability.
Maybe, I don't know. We don't go deeper in that line, and I don't know what happened, because yes, maybe we can define another measure of the amount of evolution. This is a quite simple measure of the amount of evolution, and this measure is related with the linear entropy of the energy probability distribution, but it's just a proposal, and the things come naturally. Yeah, we define this measure in a very simple way as this time average of the distinguishability, just using this expression for distinguishability, but maybe we can prove another form of distinguishability in terms of another quantifier of distinguishability between the states.
Yes, because my intuition is there is more fundamental structure between entanglement and distinguishability, and more, yes, fundamental relation. Not only for this particular measure, maybe.
Yes, of course.
Okay, thanks.
Yes.
Well, we have another question from Federico.
Hi, Anna. Thanks for this interesting talk. I have a question about the property of D, which is that it is only dependent on the length of the time interval. But does this property only holds for closed systems, or if you have a system interacting with an environment?
Yeah, I don't know, because we introduced this measure only for a pure system which evolve continually in time, and this derivation are not restricted to a discrete system. It could be any system of continuous variable, but we consider only pure state, and all derivation is in terms of pure state. Maybe it could be an interesting question, and we can work on that idea.
Yeah, because perhaps you can just check it by putting a model and see what happens, right? For open dynamics. Yeah. Okay, thanks. Very interesting.
Thank you, Fed.
Okay. Anyone have a question? Okay, well, if there are no more questions, we thank again Anna for her talk, and we continue with the last talk of the day. The next speaker is Olimpia Lombardi from University of Buenos Aires, who is going to talk about entanglement and indistinguishability in a quantum ontology of properties. We need okay, perfect. Please, when you want, you can start sharing your screen. Your microphone is off.
I have to unmute before sharing.
Okay.
Sorry. It's okay?
Yes.
Okay, thank you, Marcelo. Okay, today I will discuss the problem of defining entanglement in the case of indistinguishable case, because I don't want to talk about particles now. This paper is in collaboration with Sebastian Fortin, who is here, so we can share the answers of the questions. And well, the outline of the talk is this. It's very simple. First, I will state the problem. Then I will very briefly recall some reactions to the problem. And this will let me to introduce the ontology of properties in a very, very intuitive way. And from the basis of this, I will discuss indistinguishability in this kind of ontology. So finally, I will discuss entanglement and indistinguishability in an ontology of properties. So let us state the problem. Well, we know that the state of a composite system is entangled if it is not factorizable in terms of the product of the states of the component systems. In general, this is the definition in the case of n equal 2. In the case of two fermions, we should say that this is not entangled, but we cannot say that because we know that this state must be antisymmetrized. So we obtain, in this particular case, for instance, we obtain a state of this way, in this form. And in this case, the state is not factorizable.
No te están
sorry?
pasando las diapositivas.
No están pasando.
No.
Ops. No están pasando.
Deja de compartir y compartir de nuevo con.
Empezamos de nuevo.
Pantalla.
Empezamos de nuevo. The first time that I have problem to
Try now.
Hey, this way.
This
¿Se
is
está
the first
moviendo?
one.
No.
No, only the first one.
No
No
pongas
se está moviendo.
Tenés
No.
que poner pantalla completa y después compartir.
A ver, en general lo hacía al revés yo. A ver. No, es que si hago así no puedo presentar. No puedo compartir. No tengo manera de ir a compartir. Bueno, lo vemos así.
Sí.
Lo vemos de esta manera. This way. So now you can see the screen is moving now.
Yes, it's moving.
Okay.
Now it's moving.
Sorry. So this is these are the steps of the presentation. And now I begin by stating the problem, and the problem is how to define entanglement in the case of indistinguishable particles. And if we have two fermions, we know that we have antisymmetrized the state, so we obtain the state of this form, and this state is not factorizable, but I mean, now the question is, what happened with this state? In a recent paper, Muller and Littwater call this kind of states tangled. I mean, states that are not factorizable because of symmetrization or antisymmetrization. So the problem is to know or to answer the question whether tangled states are entangled or not. So which are the better known reactions to the problem? In a very, I mean, traditional paper Lévy-Leblond says that tangled states are entangled. Some people think that because they are not factorizable, they are entangled. But the problem is that tangled states do not give rise to the correlations that we expect to violate Bell's inequalities. The probability distribution associated with them factorizes. They are fully compatible with local hidden variable models, and they cannot be used as resources for quantum information as legitimate entangled state. I mean, they can be used, but not in the same way as legitimate entangled states. In a very, very well-known paper by Ghirardi, Marinato, and Weber, they clearly say, not with this terminology, because they don't use tangled, but they are saying something that can be said in this terminology, that tangled states are non-entangled. Which is the criterion that the authors use. They say that two systems are non-entangled when they possess a complete set of properties. In this sense, they say that even if one cannot say that particle 1 has a complete set of properties and particle 2 has a complete set of properties, because we cannot use labels 1 and 2, therefore, we can say, meaningfully say, that there are two particles, each one with its complete set of properties. Another reaction to the problem is that given by Ladyman, Linevo, and Bigach in a previous paper of that named that tangled, and they say that the entanglement of tangled states is really apparent and has no physical significance, because it is just a result, an artifact of a surplus structure of the Hilbert space formalism. The fact that we need to let aside the non-symmetrized states or non-antisymmetrized states. So instead of using a tensor product, they use a wedge product. I will not define this here, but it's well-defined. It is well-defined. So they prove that if I take something like this, a tangled state like the one I began, that is clearly, tangled, it is not factorizable because of antisymmetrizing. If I translate it in terms of the wedge product, I obtain a factorizable state. I can factorize the state in terms of the wedge product. So instead of thinking of factorizability in terms of the normal product, they use the wedge product, the normal tensor product. Now, all these views have a common feature, that is that indistinguishable is considered as a relation between particles. What is, they are, particles of the same type, used by philosophers, or identical particles, as physicists used to call them, but it is a relationship between particles. And the shortcoming in our view is that they treat distinguishable case and the indistinguishable case in different ways. The question is that if we can offer some framework that supplies a unified view valid for both cases, the indistinguishable case and the indistinguishable case, and this is what we try to offer with our proposal. So what is our ontology of properties? When we work in a Hilbert space formalism, the system is represented by the Hilbert space, and we have the primary elements are states of systems, states of particles, and secondary elements are observables which are applied to states, and they are considered as properties of systems. In the algebraic formalism, it's the thing is the reverse. Systems are represented by a star algebra of observables. So the primary elements are the observables, the properties, and states and secondary elements, which are only expectation value functionals on the algebra of observables. I mean, their role is to compute expectation values. They have no other meaning, ontological meaning. So the Hilbert phase formalism with states attached to particles and observables as properties suggests an ontology of individuals and properties, a traditional, say, Aristotelian, if you want, or Lockean ontology. The algebraic formalism, on the contrary, suggests an ontology of properties, where properties are primary, and in any case, if we can talk about objects, the objects that are, if you want, bundles of properties. So we are based on the algebraic formalism, and the idea is intuitively this way, this one. Let us suppose that we have a system that is a non-individual bundle of properties. It's a bundle of, we can discuss later. It's a bundle, but it's not like a traditional bundle theory where bundles form individuals, because if they were individuals, we had the same problems as always in quantum mechanics with the concept of individuals. So these are completely bundles that are not individuals at all. So they have no principle of individuality. I mean, they have not a principle that gives them synchronic identity nor diachronic identity. They have no individuality principle that make them different than another bundle and different from the same bundle in different times. The same bundle. I mean, that may let you identify the bundle in different times, as happening in quantum mechanics. So now, what is indistinguishability from this view? If we have indistinguishable bundles, now the colors and the symbols are very trivial. I mean, the same color is the same. A color is represented in observables, and the symbols the eigenvalues. If we have indistinguishable bundles, so when we form a new, when they come together to form, to combine and form another system, that system is a new bundle where the original bundles cannot be re-identified. So this is a unique entity where the identity or the individuality of the original bundles gets lost. I mean, they don't get lost because they were not individuals from the very beginning. They are completely and absolutely bundles. So the peculiarity of the case when the bundles are indistinguishable is that this new bundle now is symmetric, just by construction. So in this case, when we think about the principle of identity of indiscernibles, the Leibniz principle that is very discussed in the case of quantum mechanics, the principle says that two individuals that have all the same property, all the properties in common, they are the same individual. This principle is not false. The fact is that it does not apply at all, because indistinguishability is not a relation between individual particles. I mean, the principle of identity, the Leibniz principle, is a principle that applies to individuals. Those individuals designed by these individual variables, precisely logical individual variables. So now we have no individuals. So the principle does not apply, because indistinguishability, that is not a relation between individuals, is an internal symmetry of a single composite bundle. So it changed indistinguishability changed its meaning from the very beginning. What happened with indistinguishability? So in this ontology, let us assume that they are not, that systems are not individual but bundles, and they are represented by spaces of observables. And if we make an aggregate of two bundles, we form another bundle whose observables have this form, and this is the general form of a generic observable of the composite bundle. But the fact is that the operation of aggregation of bundles, when it is applied of indistinguishable bundles, is commutative. This is very natural. If the bundles are indistinguishable, it doesn't matter which I take first and then which I take later, so I can permute the order in which I take them. So this led to the fact that any observable of the new bundle must be represented by this symmetric matrix with respect to the permutation of the indices alpha, beta, m, and n coming from the two original bundles. So again, indistinguishability is no longer a relationship between individual particles, but an internal symmetry of the whole closed system that is manifested by the fact that its observables are symmetric. What about symmetric states? Let us consider states, density operators. Any operator can be written as a sum of a symmetric part and antisymmetric part. This is the meaning of symmetric part and antisymmetric part. So when I make the expectation value of any observable of the system, the composite system, the system composite of indistinguishable bundles, and I make the trace, when I decompose the state into the symmetric and the antisymmetric part, the antisymmetric part has no effect on a symmetric observable. This is a mathematical result, of course. An antisymmetric operator on a symmetric operator, the trace is 0. So the fact is that the symmetry of the operators representing physical states of aggregates of elemental particles, bundles composed of original bundles that are indistinguishable, is not the result of an ad hoc symmetrization, but it's due to ontological reasons. That is the very structure of the ontology that makes natural that indistinguishable bundles, when composed, can be permuted. So how to understand the indistinguishability principle in this case? The traditional formulation of the indistinguishability principle is in terms of states. For any state of a composite system whose components are indistinguishable particles, the expectation value of any observable must be the same for that state and for the permutation of the state. This is the normal or traditional formulation. Nevertheless, this form of the principle establishes a restriction on the states of the composite system. On the other hand, the principle can be formulated in terms of observables. for any observable of a composite system whose components are indistinguishable subsystems, in this case, bundles, its expectation value in any state must be the same for that observable and for the permutation of that observable. In this case, the principle establishes a restriction on the observables of the composite system. I have to retain only the observables that are symmetric. And this is something that it's in the literature of the subject. I mean, we are not inventing this formulation. What I mean is that from the viewpoint of an ontology of properties, this is not the version of the principle that makes sense, but this one is the principle that makes sense in this context. So, what happened with entanglement and indistinguishability in this kind of ontology? What happened with entanglement is something that when this point is discussed, when entanglement in indistinguishable particles is discussed, these general features of entanglement are usually not taken into account. Let us take them into account. First, interaction is not a requirement for entanglement. We know that there is entanglement swapping. Entanglement is not a relation between particles. This is something that there is very clear in the literature, in the physical literature. There is intraparticle entanglement. And entanglement, there is entanglement of, by contrast, in general, people talk about entanglement of indistinguishable particles by contrast with these results in physics. And more important, entanglement is relative to the particular decomposition of the composite system. For instance, in a very cited paper, it is said, entanglement is a property of a quantum state relative to a given set of subsystems. A question like, is there entanglement in such state, is meaningless in isolation. This is something that has been discussed, for instance, by John Ehrman a lot, not in the case of distinguishability, but in the case of definition of entanglement. So the problem is that in the case of indistinguishability, we have no tensor product structure. So this is the problem in this case. So these kind of features are not taken into account in the discussions about entanglement and indistinguishability in the philosophical literature. So we want to take into account and show that from the viewpoint of an ontology of properties, these are normally taken into account. From our ontology of properties view, entanglement, we say, is not a relation between particles because there are no particles. Systems and subsystems are bundles of properties. So entanglement is given by a kind of correlation between properties, not between systems. Entanglement is relative to the decomposition. Which decomposition? The composition of a system, but the system now is represented by an algebra of observables. So entanglement is relative to the decomposition of an algebra into some algebra of observables. And this kind of algebraic approach to entanglement is something that is present in the physical literature. For instance, there are two papers by Balachandran and collaborators, but since then it was presented in other papers. And the idea is that instead of talking about reduced state, the reduced state needs to use, we need a Hilbert space structure to define a reduced state. They replace the idea of reduced state by the idea of restriction to a subalgebra. A state is a restriction to a subalgebra when this happens. The expectation value in the original state is the same as in the restricted algebra in the restricted state. The idea is to use, in a certain sense, the very definition or the main idea of the reduced state, but not with the definition of the reduced states in terms of Hilbert space. In terms of operations on the Hilbert space, on states of the Hilbert space. So, with this definition, a pure state on a certain algebra or subalgebra is not entangled with respect to the partition, no, in terms of a certain algebra, to the partition, sorry, this should not be the one, to a certain partition if the restrictions are also pure. The idea is that instead of thinking about reduced states with the traditional definitions or traditional ways of computing and say, if the reduced states are pure, so the states, the composite states is not entangled. In this case, we use the concept of restriction or to a subalgebra that is a generalization for a partition of complete algebra in subalgebras. In this case, we have no problem if we have not the structure of this Hilbert space. We have a structure that we have not in the case of indistinguishability. So, which are the conclusions? From this viewpoint, entanglement is not a relation between particles, but it is a specific property of the state of the whole composite system that encodes particular correlations between properties, those correlations which violate Bell's inequalities. Indistinguishability is not a relation between particles, but an ontological motivated symmetry of the whole composite system. So, in the case of indistinguishability, entanglement does not require the symmetrization of the state. We have the symmetrization of the observable, but this is due to ontological reasons. It's not an ad hoc symmetrization or anti-symmetrization of the states. And this gives a unified view of entanglement. Thank you. These are papers on the ontology of properties, previous papers here, and this presentation is based on this last paper that I hope that very soon will be published in Studies in History and Philosophy of Science in the section of physics. So if somebody wants to read it before publication, I can send it. Thank you.
Okay, thanks Olympia for your talk. Now we have time for questions. Anyone have a question?
I can stop here.
Okay, Dennis.
Thank you, Olympia. Very interesting talk, and you will not be surprised that I agree with many things that you have been proposing and saying. I've actually several questions, but the first question is, you want to do without any particles, and you want to replace the particle concept with a bundle of properties. But I was wondering when I saw your presentation whether you don't assume something like a particle already from the start, because you seem to think in terms of an algebra that's split up in sub-algebras. And all these sub-algebras will bind certain operators and properties together. And normally one would call such a sub-algebra as something that corresponds to a physical system, and in particular a particle. So don't you smuggle in the concept of a particle via the back door?
Thank you, Dennis. Thank you. This is a very good question. When I talk about particles, I'm thinking about individuals in the philosophical sense. I mean, we have systems, but those systems do not behave as individuals, as traditional individuals, so that you can put them together and then re-identify them in the composite system, and then that you can count them in the composite system, and that you can re-identify them through time, and that you can label them. So all these traditional, classical views, the classical features are not present in this case. So we can talk about particles, but we have to clarify that they are not classical particles. They are quantals, if you want. This is why I talk about systems and not about particles, because when we talk about particles, it seems that we are talking about objects. There is something very interesting that about how to talk, how to formally handle this kind of items that are not objects in the classical sense. And well, we have written a paper, and we have trying to finish it, trying to use quasi-set theory to treat not as originally. This is a paper with Decio Krause and Federico Holick and Juan Pablo. But the point is that we are not using the quasi-set theory as originally Decio Krause does, but the items are not non-individuals representing systems. The items are properties. So when I talk about a bundle of properties, this is a quasi-set, because we have not even a logical language to talk about properties in this way. And we needed, even if we think like your talk the other day, we think in substances, mass, the reference of mass terms. We also need a kind of new logics to talk about this. It's completely different from traditional individuals.
Okay, thank you. That helps. Can I ask something else, or is the...
Yeah, you can.
Yes, one other thing. So you derived, as a kind of very plausible and natural thing within this properties framework, that all the states, I mean the density operators, the density matrices, must be symmetrical. But it seems to me that that's weaker than what's used in the ordinary particle picture, where you have fermions or bosons, and the states of the one are anti-symmetrical and the others are symmetrical. But if the total states, the density matrices are symmetrical, I think there are more possibilities than these two things.
Well, we are not considering parastatistics, but the case of symmetric states or anti-symmetric states both give symmetric operators. The symmetric operator can come from a symmetric, I mean, you will have symmetric observables which are fermionic and which are bosonic. This is, I mean, it's a subtle point, but both as observables, I mean, as operators, are both symmetric, but they operate in a different way if they are bosonic or if they are fermionic. But as operators, they are both symmetric as operators.
Yeah, sure. Yeah, so I understand, right? So do you understand that you do not exclude, or you cannot exclude on the basis of your formalism that there are states that are either symmetric or anti-symmetric?
No, I will send you the paper. This is very, very well explained there. Yes. No, we don't exclude that. No. Thank you.
Thank you very much for your
the opportunity to explain that.
Thank you.
Okay, we have another question from Ariel Castillo.
Okay, very good. Sorry, but I don't have a camera right now. I will on Friday when I give my talk. Let's see. I was just curious. All this discussion about indistinguishable particles, particularly fermions, is based, or rather becomes confused by the fact that these are supposed to be indistinguishable objects, and you have a Pauli exclusion principle and all of that. Good. This is what I'm curious about. Have you considered the possibility of using something like a field definition of fermions, something along the lines of what Jordan and Wigner did back in the day, in which the model one uses to describe these fermions is almost like a space is like a computer screen. Each volume element is a pixel. The pixel can be on or off, but it can only be on once. You cannot put two ons on the same pixel. It's either lit or not. It doesn't make any sense to have two of these particles at the same pixel. So this would be a model in which the exclusion principle is automatically taken into account. Obviously, the system is the whole of space, the excitation of the whole field, the state of all the pixels. And so I was wondering if you have thought about, your formulation in terms of the ontology of properties in such a system where the concept of particles emerges, but and not emerges in the philosophical way, but there is a concept of particle in which each pixel is localized, but the identity makes absolutely no sense. They're automatically indistinguishable, right?
Yeah.
Have you thought about those lines?
Well, thank you for your question, because it allows me to say something more. I don't know. I never heard about that model, but I think that model is to explain the exclusion principle. But the fact is that our view applies to fermions and to bosons. So this is not the problem of the exclusion principle. It's the problem of indistinguishability. Nevertheless, what you say about the excitation of the field, this is very relevant, because this view, this proposal is a proposal for interpretation of non-relativistic quantum mechanics. I'm not talking about quantum field theory. Nevertheless, I think that it is much easier to extrapolate a view of, a picture of an ontology of properties to quantum field theory than an ontology of particles. Because if I have an ontology of properties, now I can think that properties are, properties are functions of point, of space-time point. So now I have, instead of having an operator, I have an operator that it's a field, and the particle, the electron, is a field. It's a property. It's a property for each. No, a property, a bundle of properties, but the properties depend of each point of space-time. And this is not crazy, because there is an interpretation of quantum field theory in terms of bundle of properties in the field of philosophy of physics that was this. I think that it was some years later of our first paper on our interpretation, but we can say that it was pretty simultaneous. So the idea that quantum field theory is more friendly to an ontology of properties is not. It's not very natural, but I think that it's natural. So if we take the interpretation of an ontology of properties from the very beginning, just in the case of non-relativistic quantum mechanics, to go to quantum field theory, I think that it's easier. So thank you also for your question, because it allows me to say.
Okay, no, thank you. Thank you. I also agree that it is actually easier to think in terms of fields, whether you're talking about bosons or fermions, that somehow it is the particles that are the less fundamental objects here.
Yes. And it's interesting, but what is a field? A field is something that assigns properties of each point of space-time.
Correct. Yes.
So it's so natural to pass from properties to fields understood as properties on the space-time.
So then in this case, your properties would be like functionals.
Yeah.
Over distributions in space-time, which is perfectly nice. Yes.
Thank you.
Well, any other question? Well, if there are no more questions, we thank again Olympia for being here.
Thank you.
Well, we now are closing this fourth session. We thank all speakers for their contributions, and also all the participants for their attention. We will continue tomorrow at 9 o'clock from Argentina. Well, see you all tomorrow.